Hi, everybody. Welcome back to Graduate Statistics. This is week 12, and it's our lab portion. It's our second video. If you didn't watch the first one, hop in there first, where we made plots of these 6 different data sets that I created. So it's fake data to express the relationship between ice cream and happiness. But all I wanted with this piece is to show you, get you some experience looking at correlations that are strong, moderate, weak, no correlation at all, so you can get some experience with it, and then actually run the analysis to see if the numbers match up with what you expected. So we did the first one. We expected a positive, moderate relationship. We almost got it wrong because it's kind of in the borderline of moderate and weak. And if we look at the confidence interval, it goes from somewhere kind of small, correlation of 0.45, all the way up to a moderate high relationship of 0.7. Again, I'll repeat the cutoffs that I'm using. That comes from the book written by Cohen. I think it's called Statistics for the Behavioral Science, which takes coefficients between 1 and 0.8 as strong, between 0.8 and 0.6 moderate, anything below 0.6 on the kind of weaker range. But it's a bit arbitrary. We look at the coefficient and we determine whether it's reliable or not, and depending on your area, it may be an important correlation to find. Depending on your area, it might be a very weak correlation to find. And the reason I'm saying this is because, in social sciences, in areas that you guys are likely to work at, you're dealing with such complex phenomenon that I'll give you an example. Imagine disparities in health. How do you predict that? What are the kinds of explanatory variables that would relate to this, right? Because it's a multifactorial thing, it's very unlikely that any variable in isolation will have a highly strong relationship with that. But if you find, a 0.3 relationship that is reliable between, education and health disparities, it is an important thing to consider given the multifactorial nature of this. But in my area, for example, if you're trying to predict, perceptual responses under particular informational variables that participants are exposed to, and you find a correlation of 0.3, we would say that's probably not what they're using to make the predictions, to make the perceptual judgments. So it really depends on the area. This is just sort of a rough way of talking about things to get your eyes a little trained to look at those plots. But of course, the analysis actually gives you correlation coefficients, but it is important to sort of have a general expectation because things can go wrong. For example, if I saw, let's say, if I saw a negative relationship here, negative coefficient here, I would be like, what? Did I input the data correctly or not, right? So you pick mistakes that way. All right, so for data set 2, the point estimate was 0.95, so strong and positive as we expected. And you can see how the confidence interval is really tight too. Even the lower end suggests a high correlation. And to remind you of the syntax, here we had to change just the data set name because the variable names are the same inside of all of our data sets. But here, the data set 2 is called happiness 2, not happiness, so we had to change that. All right? And I didn't change the name of the model, but you could change that too, call it happy 2 instead. So you keep creating different objects there. So if you need to get back to it, you can. This is the correlation for the third data set. Note that I'm using happiness 3, that's very good. And we predicted there a negative moderate relationship. And on average, we got that right. But the confidence interval suggests that it could be, with 95% confidence, somewhere between 0.51, which technically would be on the low correlation side by the criteria we're applying here, all the way up to almost strong, like moderate high, let's say. For the next data set, happiness 4, we predicted a strong negative correlation, and here And you can see how this is significant as well. I forgot to mention that. We predicted a strong negative, reliable, statistically reliable correlation. So we're dismissing the null hypothesis that, you know, the relationship is zero in the population, that rho is zero. It's negative 0.95 and somewhere between 0.93 and 0.97. So very strong, as expected. Next data set, we predicted no correlation. And indeed, you can see how we cannot dismiss the null hypothesis. We cannot accept the alternative hypothesis that the true correlation is not equal to zero, because it's very likely to observe a t magnitude of negative 0.22 or larger, or under the null hypothesis. And you can see how the point estimate is that the correlation is practically zero, and the confidence interval goes from negative 0.21 to 0.17 with zero in the middle. That's what makes this non-significant, right? It's consistent with this being not significant. Last one, let's look at, we looked at a weak correlation coefficient. It's reliable, but weak, right? It's a negative weak correlation. So somewhere between negative 40 and pretty close to zero, right? So reliable, but the importance of it depends on the field again that we talked about. All right. Now we're going to move on to regression. We're going to model the relationship between these two variables. What regression will tell us when it estimates the slope of the line is how much I can expect someone's level of happiness to be given how much ice cream they eat, right? So today we'll only focus on the part of the output that describes the relationship between one outcome variable and one predictor variable, but we'll do with multiple predictors next week. That'll be fun. So the basic regression equation, linear regression equations you learned when younger, was probably y equals mx plus b. We'll use this notation here. But you could think about this as the beta 1 and the beta 0, b being the beta 0, the intercept, and m being the beta 1, right? So that's the equation of a line. And this is, you know, y is the value of outcome or response variable. M is the slope. X is the variable used to predict y, the explanatory variable or predictor. I should do explanatory or predictor. And B is the intercept. So back to our example. Let's describe the relationship, but now let's add a line to the plot. And to add a line to the plot, I'm simply adding this, layering the line on the plot by doing the plus trick. Plus, and then I use this geom smooth function, and I say that I want as a method to fit the line, the linear model. So I want to fit an equation of a line here, and it shades out the confidence interval of the predictions, right? And this is the shaded thing. So when you say, oh, how much can I predict happiness to be if people eat 3 ice creams a week? Well, the prediction, you have to go all the way to the line and cross back, but you know that your prediction could be off by the gray area here, okay? So it's kind of setting a confidence interval on your predictions. All right, so here's the model that we're gonna try and estimate. This is illustrated here. The model is illustrated by the line. Now we're gonna actually get the parameters of the line. So I'm gonna give the model a name, happy model. You can give it any name you want. Then we're gonna use the LM function, same that we use for ANOVAs. Then we have our dependent variable or response variable first, that's important. And we have the squiggle, and we have the predictor or explanatory variable second. And then we're using dataset 1, happiness. And now we're gonna ask for the model summary. And what we see here, testing our hypothesis using t is that the R square of the model is 0.36. That means that ice cream consumption explains 36% of the variance in happiness in this fake data set. And that makes sense because our confidence, if you take the square root of that, you will get our 0.6 coefficient that we estimated. It has a significant p-value suggesting that our model is doing something reliable. It helps. If you want to know about happiness, it helps somebody's level of happiness. It helps to know how much ice cream they eat because the model is significant. So you can test that using the F statistic as we talked about. So we get the p-value for the model as a whole. Now let's look at the estimate of the slope and the intercept. So the slope, the intercept is 2, and the slope is 0.6. It's important to look at the significance of this one. It's not really critical to look at the significance of the intercept. It just says that, the intercept is not 0. It's not really interpretable here. What we really want to know is the slope different from 0? Remember? So you have the estimate of the slope. If you divide that by standard error, you get the t, and we want to know the probability of getting this value of t or larger if b was actually 0, if beta, right? If the slope in the population is actually 0. And we see here that the probability is really low of getting this magnitude of t under the null hypothesis. So we dismiss the null hypothesis that ice cream is not a good predictor of happiness, all right? So again, the F statistic will, if the F statistic is significant and you have a simple regression model, chances are that this will also be significant, but because what else could be explaining the significance of the model? But these two may become together informative at multiple regression because you can have a full model with an R square that is significant, saying that, this model is helping predict our response variable, but maybe not all variables in the model will be contributing to it. So it is important to look also at what's happening in this model. Just practice doing that because it will be important for next time. Okay, so one more time with Philip. Question. Identify the slope and the intercept estimates. So the slope is 0.6 and the intercept, let's change that bit. The intercept is 2 and the slope is 0.6. Interpret the slope. For each unit change in ice cream consumption, if I go from 1, if you have somebody that ate 1, somebody that ate 2, their level of happiness is expected to differ by 0.60 units. Yes? 0.60 units, right there. Write out the regression equation. Happiness predicted. You could do happiness with the hat, right? But because it's hard to program that out here, I just do happiness predicted. The predicted happiness equals the intercept, which is 2, minus, or plus, 0.60 ice cream, right? That's what it is. Cool. So now when we come back, we're going to learn how to make predictions using R. All right? See you then.